The warm return, chilled water, only enters the evaporator where it passes along the outside surface area of the inner tubes, which contain the refrigerant. It then exits at the opposite end, having given up its thermal energy. The refrigerant is the only fluid which moves around each of the components of the chiller. It changes its pressure, temperature, enthalpy, and entropy as it moves around the machine and transports the unwanted heat away from the evaporator. Chilled water. The air-cooled chiller has 5 main components. 1. The compressor, typically screw, scroll, or reciprocating. 2. The condenser, a bundle of horizontal pipes which contain the hot refrigerant. These are surrounded by a number of thin sheets of metal in the vertical axis. These help distribute heat away from the tubes and into the air, which is blown across the tubes and thin sheets of metal. 3. Condenser fans. These suck air across the condenser coils, entering from the sides, and then force this air at the top of the unit upwards into the ambient atmosphere. 4. Expansion valve. This expands the refrigerant before it enters the evaporator. 5. Evaporator. This is where the chilled water is produced and the heat from the warm return chilled water is extracted to be sent to the condenser. Water-cooled chiller. Water-cooled chiller systems have a cooling tower, thus they feature higher efficiency than air-cooled chillers. Water-cooled chillers are more efficient because they condense depending on the ambient temperature, bulb temperature, which is lower than the ambient dry bulb temperature. The lower a chiller condenses, the more efficient it is. This system has several essential components including cooling towers, condenser water pumps, makeup water pumps, chillers. In the evaporator. The role of the evaporator is to produce chilled water. The device releases the water at about 6 degrees Celsius, 42.8 degrees Fahrenheit, and pushes it throughout the facility with the help of a pump. A network of pipes passes the chilled water through every necessary section of the building. After exchanging coldness with room air, which blows across the air handling units, AHUs, and fan coil units, FCUs, the water is now warmer at about 12 degrees Celsius, 53.6 degrees Fahrenheit. It returns to the evaporator where the refrigerant absorbs the unwanted heat and directs it to the condenser. The chilled water is cool once again, and it can now continue to cool the facility. Note how this is called chilled water throughout, no matter the temperature. In the condenser, a refrigerant brings unwanted heat from the evaporator and passes through the condenser. There is another loop connected to the condenser water loop, which is between the cooling tower and the condenser. After entering the condenser at about 27 degrees Celsius, 80.6 degrees Fahrenheit, the water leaves at 32 degrees Celsius, 89.6 degrees Fahrenheit, and heads to the cooling tower. Note that at no time do the refrigerant and the condenser contact directly. Heat exchange is only through a pipe wall. The Condenser water, with the unwanted heat, goes to the cooling tower for further heat rejection. In the cooling towers, this is where the unwanted heat in a facility ends up. A large fan feeds the unit with air. The air meets with the oncoming condenser water. From the direct contact, the condenser water loses heat to the air. The condenser water goes back to the condenser. The cycle continues. Air conditioning equipment capacity range, TR. Air-cooled equipment. Water-cooled equipment. Ventilation. Ventilation is the process of exchanging or replacing air in any space to provide high indoor air quality, which involves oxygen replenishment and removal of moisture, odors, smoke, heat, dust, airborne bacteria, carbon dioxide, and other gases. Ventilation is often refers to the intentional delivery of the outside air to the building indoor space. Method 1. Natural ventilation. 2. Mechanical ventilation / forced ventilation. 1. Natural ventilation. Natural ventilation is the process of supplying and removing air through a space by a natural means. It can be achieved with openable windows or vents. 2. Mechanical ventilation. Mechanical ventilation is also called forced or induced ventilation, and is done by fan and other mechanical means. ACH, air change per hour. Air change per hour is the number of times that the total air volume in a room or space is completely removed and replaced in an hour. Duct. The conditioned air, cooled or heated from the air conditioning equipment, must be properly distributed to rooms or spaces to be conditioned in order to provide comfort condition. When the conditioned air cannot be supplied directly from the air conditioning equipment to the spaces to be conditioned, then the ducts are installed. The duct systems convey the conditioned air from the air conditioning equipment to the proper air distribution points or air supply outlets in the room, and carry the return air from the room back to the air conditioning equipment for reconditioning or recirculation. The duct are usually made from galvanized iron sheet metal, aluminium sheet metal, or black steel. The most commonly used duct material in air conditioning systems is galvanized sheet metal because the zinc coating of this metal prevents rusting and avoids the cost of painting. The aluminium is used because of its lighter weight and resistance to moisture. Examples: supply air duct, return air duct, exhaust air duct, and fresh air duct. Supply air duct, it is used to supply air into the room. Return air duct, it is used to remove the air from the room to maintain pressure inside the room. Exhaust air duct, it is used to remove smoke, odor from the kitchen and toilets. Fresh air duct, it carries the outside air. Types of duct. Based on shape. 1. Rectangular duct. 2. Round duct. 3. Square duct. 4. Oval duct. Based on pressure. 1. High pressure. Static pressure is in between 150 mm to 250 mm of water. 2. Medium pressure. Static pressure is in between 50 mm to 150 mm of water. 3. Low pressure. Static pressure is less than 50 mm of water. Based on velocity. 1. High velocity, velocity 750 m/min. 2. Low velocity, velocity up to 750 m/min. Types of joint used in duct system. 1. Slip joint. 2. Drive slip. 3. Flange joint. Duct design method. 1. Velocity reduction method. 2. Equal friction method. 3. Static pressure regain method. Pressure losses in duct. 1. The pressure is lost due to friction between the moving particle of air and the interior surface of the duct. 2. When pressure loss occurs in the straight duct, it is termed as friction loss. 3. When pressure loss in elbows, bends, etc., it is termed as dynamic loss. The thickness of the GI duct sheet. 1. As per Schmackner, the gauges of the duct sheet depend upon the width of the duct and type of application of a particular project. 2. Schmackner stands for Sheet Metal and Air Conditioning Contractors National Association. 3. Here are the few gauge system as per Schmackner. A 26 gauge is used for the duct size below 300 mm and thickness is 0.5 mm. B 24 gauge is used for the duct size above 300 mm to 750 mm and thickness is 0.6 mm. C 22 gauge is used for the duct size above 750 mm to 1200 mm and thickness is 0.8 mm. D 20 gauge is used for the duct size above 1200 mm to 3000 mm and thickness is 1 mm. E 18 gauge is used for the duct size above 3000 mm and thickness is 1.2 mm. F 16 gauge is used for the machine cabinet and thickness is 1.6 mm. Formula to find the area of ducting. 1. Circular duct area equals 2 RL. Where R equals radius of the circular duct. L equals length of the circular duct. 2. Square duct area equals for AML. Where R equals sides of the square, all sides are equal. L equals length of the square duct. 3. Rectangular duct. Area of straight piece equals 2 W plus H L. Elbow duct area equals 2 W plus H L2 plus 2 W1 plus H1 L1. Transition duct area equals 2 W plus H L W plus H dash RL. Offset duct area equals 2 W plus H L1 plus L2. Reducer duct area equals 2 W plus H L W plus H dash W1 plus H1 L.